So we're going to look at a distribution of sleep data. This is how long people sleep. And if you take a look here, our population size is 18,000. So a pretty substantial group of people, pretty big sample population or sample of people, however you want to regard it. But what we want to do is we want to play around with this a little bit. We're going to take a sample of size 9 from this population. So at random, we're going to draw out 9 individuals and look and see how long did they sleep. And then from there, calculate the average. And then we're going to repeat that 1,000 times. So you should check this little box here. It says show sampling information or show sampling options. Type in 1,000 samples of size 9. Now, before we do that, before I hit the draw samples button, let me make a couple bold predictions. The mean of this distribution, well, the mean of that distribution is about 8.001. So about 8 hours of sleep that people are getting on average. I know that I'm on the left side of this curve. I think my kids are far to the right, but whatever. Let's see what else. The standard deviation is 1.51. Okay, so about 1.5. What does the standard deviation tell us about a distribution anyways? Anyone?
How far the values are spread apart from the mean.
Perfect. How far the values are spread apart from the mean. In this case, we got a standard deviation of 1.5-ish. So I'm going to predict that if we draw 1,000 samples of size 9, that the average of those samples is going to be pretty close to 8. But the standard deviation is going to be pretty close to 0.5. Now, your numbers might be different a little bit than mine. That's okay. Let's draw the samples. And there they are. And let's take a look at how they stack up. Was the mean of this distribution, the mean of these sample means, is that pretty close to what I started out with here?
Yep.
Yeah. 0.7 or 7.982, that's pretty close to 8. How about the standard deviation? Was I correct in my prediction there? I said about 1/2. That's really close to 1/2. So, wow, maybe I should play the lottery tonight, right? What do you think? How about the shape of this distribution? What does the shape of that distribution look like?
Bell curve.
Yeah, a bell curve. Thank you, Skylar. A bell curve or a normal distribution. So, nice, nice.
I got different mean standard deviation than you.
That's okay. Everybody's is going to be a little bit different, but the numbers should be generally close to what we've got.
Okay.
Is that what you're seeing? Something close to what I got? Okay, good, good. Let's change our sample size. Instead of drawing samples of size 9, let's draw samples of size 16. Now this time, I'm going to go out on a limb again and make a different prediction. This time, I think that the standard deviation is going to be about 0.375 instead of 0.5. But that the mean is still going to be close to the same. Not bad, not bad. So standard deviation 0.366, not quite 0.375, but close. And the mean, again, was very, very close at 7.933. Did anyone get it exactly? Did anyone get 8.001? Well, that's okay. I didn't expect to get it exactly because the mean is a random variable. And everybody's going to have different experiments. So your distribution should look similar to this, but might not look exactly like this. Again, this looks like a normal distribution. Let's try this one more time. This time with samples of size 25. This time, I again predict that the mean is going to be near 8, but this time the standard deviation is going to be near 0.3. Not bad. Now, each time we do this, we got a distribution that looked, pretty normal. But then again, we started out sampling from our parent population, which also looked normal. Let's pick a population or pick some data that doesn't come from a population with a normal distribution. Yeah, with a normal distribution. So go up here and let's scroll down to pennies. And when you get that, so when you scroll down to pennies, click use data, and it should come up with a distribution. Does that distribution look normal? What do you think? Is that a normal distribution?
It's
Nope.
skewed to the left.
Yeah, it's skewed to the left. It looks pretty far from normal, to be very honest. But we're still going to sample from that distribution and see what happens to the distribution of our sample mean. And we're going to start out small this time. Let's do samples of size 2. So we're going to calculate 1,000 samples of size 2, and actually we should draw 1,000 samples of size 2 and calculate their mean and see what we get. And here I go. So, okay. Is this distribution normal or no? Not exactly. What direction is it skewed?
To the right.
Michal,
Left
which
still?
direction is it skewed?
I
Oh,
said it
all
was
right,
going-
Jacqueline, either one.
I said it's going towards the right.
The skew is where the tail is. So where's the tail? Is it on the left or on the right?
So the tail's towards the left.
Tail's towards the left. Good. So this is skewed left. So it's not quite a normal distribution, but it doesn't look too bad. Let's increase our sample size a little bit more. And I forgot to make my prediction on the last one, so let me make a prediction on this one. With samples of size 4, I'm expecting that the standard deviation of our new population should be about 4.8. Let's see if I'm right. Not bad, not bad. Same mean, roughly speaking, but different standard deviation. It's pretty close to that 4.8 that I expected. Now we can keep on playing this game. Let's jump up to samples of size. Let's just jump up to samples of size 25. This time, I think our standard deviation is going to be about 1.8. Let's see. Yeah, about 1.8. All right, 1.93. Not bad, not bad. But what we've got looks pretty much like a normal distribution. So nice. And what this is saying and what this is showing is that regardless of what you start out with in terms of an initial sample, if your sample size gets big enough, the sample mean is going to have a normal distribution. Let's take a look at that with your handout. So this is section 6.4. And here's what happens when you look at an original population. So this is your, what I call parent population, no relation to me. These are our original populations. Let's just focus on these two. If I take a sample of size 2, if I take all possible samples of size 2 and calculate the distribution of that sample mean, that new random variable, then this is the distribution that I get from this population. If I sample from this population for samples of size 2, I get this. Are either one of these normal looking distributions? No, not really. How about if I take samples of size 10? Are these looking like normal distributions?
More normal.
More normal. And when you get to samples of size 30 or more, they're looking even more normal. In fact, they look pretty
Equal.
much exactly like a normal distribution. You can do this with any distribution you want, no matter how ugly they look in the beginning. When you sample from these distributions and your sample size is big enough, eventually they're going to look like a normal distribution. What if you start with a normal distribution to begin with? If I sample from a normal distribution and calculate the mean or the distribution of sample means for samples of size 2, does that look normal?
Yes.
Yeah. And that looks normal, and that looks normal. What is changing though, as I go from this one to this one to this one to this one? What characteristic of this population is changing?
The standard deviation.
Ah, well done. Thank you, Keisha. The standard deviation is changing. It's getting smaller, which is why these distributions are less spread out and more concentrated around the population mean here. The conclusion that I want you to get is kind of twofold. Now in calculus, there's the fundamental theorem of calculus that talks about the relationship between a function and its derivative. In college algebra, they have a fundamental theorem of college algebra that basically says that polynomials of degree 5 have 5 solutions. Here's our fundamental theorem for statistics. It's the central limit theorem. And I've boiled it down this way. We're going to look at some random variable x, and I'm going to say that x has a distribution. X is distributed with a mean of mu and a standard deviation of sigma. Now, it doesn't have to be a normal distribution. A lot of times it is, sometimes it's not. But this is my parent population. This is where I'm sampling from. This graph showed us two things. The first thing it showed us is that no matter what distribution you start out with, if your sample is big enough, then the sample mean is going to have a normal distribution, or at least an approximate normal distribution. So x bar sub n, what I mean by that is the sample mean for samples of size n. Yeah, let me do that. Sample mean for samples of size n. Okay. If I'm drawing from this population and calculating the sample mean, this random variable will be distributed approximately normally with the same mean, but the standard deviation is going to be sigma over the square root of n. That's the big thing here. So what it's saying is no matter how awful your distribution is to begin with, this random variable is going to have a normal distribution for large enough sample sizes. Always. And our magic cutoff is samples of size 30 or more. And then do you want to include 30 or not? It's not going to really make a big difference. So that's one possibility. The other possibility is that I could sample from a normal distribution to begin with. And if I sample from a normal distribution to begin with, then at every stage, regardless of n, I'm going to have a normal distribution. So if I'm sampling from x, which is distributed normally with a mean of mu and a standard deviation of sigma, if that's my parent population, then for samples of size n, I'm going to have the same mean. The standard deviation is going to be sigma over the square root of n, just like it was up above. It's just that here, I don't have to worry about n being greater than 30. I'm always going to get a sample mean with a normal distribution. That's assuming that I started out with a normal distribution. So I want to look at this for two different sample sizes and a given population. Before I do, are we okay with what I've got here? We're going to do a lot of examples, I hope.
Wait, what's the difference between the first one and the second one? I mean, I know I see an N, but
Yeah, the first one, this does not have to have a normal distribution. This could be any distribution.
oh, okay.
Any distribution. Whereas this has a normal distribution to begin with. So here you're sampling from any distribution. So it's like either of these second pair here. These are non-normal distributions to begin with. So that's where you're drawing your sample. But if your sample size is large enough, eventually it's going to look like a normal distribution. And you can use the probabilities from the normal curve because of it. The second part says, all right, we're going to start with a normal distribution. With a normal distribution. And if you start with a normal distribution, you don't have to worry about n as being greater than 30. All these samples of size n are going to have a mean with this distribution. It's going to be normal with that mean. So I'm not sure if this is something I've pointed out carefully enough. This mean and that mean are going to match. This standard deviation divided by the square root of n, that's how you get this one over here. So let me share with you this example down here. I'm going to start with a normal distribution with a mean of 100 and a standard deviation of 10. So this is my parent population. And then from that, I want to draw samples of size 10. Now, before I draw my samples of size 10, let me highlight which distribution I've got here. And it's this one that's kind of really spread out down here at the bottom. It's that one. Let's see what things look like if I took a sample of size 10 from this population. Now keep in mind that that's my mu and that's my sigma. For n equal 10, this is just a number that I'm choosing because I did the handout. For n equal 10, samples of size 10 have a mean with the following distribution. The mean here and the mean here are going to be the same. They're going to be 100. But how about the standard deviation? What's going to change over here? Well, it's supposed to be sigma divided by the square root of n. So 10 over the square root of 10. That's my new standard deviation. If you're to simplify this with some of the algebra I was mentioning earlier, that's just the square root of 10, about 3.16 maybe, I'm not sure. Let me just take a look here while I'll let you copy. Square root of 10, yeah, about 3.16. Which curve is going to be more spread out? This curve or this curve? The parent population or the one where we sampled and drew samples of size 10? Standard deviation measures how spread out things are. If you have a bigger standard deviation, are you more spread out or less spread out?
More.
More. So this one should be more spread out than this one. And that's this one right here. Now I'm choosing these numbers, not exactly at random, but out of convenience. And again, they're chosen to match what we have here on our handout. On an exam, you'd be given these numbers or you'd be able to figure that out from the problem. But let's do one last problem and one last part of this. And that is, let's look at samples of size 100 and figure out, well, how is X bar for samples of size 100 distributed? There's two things that I want. Both of them come from this part right up here. Actually, I guess this part right here. Try and figure out what's the mean of this distribution and what's its standard deviation. All right, somebody help me out here. What's X bar sub 100 going to look like in terms of its distribution? Anyone?
100.
All right, it's going to have a mean of 100. Good. Because its mean is going to match the mean of the original distribution, our parent population. What about the standard deviation? What do I got to do to calculate that?
10 over the square root of 100.
Perfect. So 10, which is sigma from the parent population divided by the square root of the sample size. So 10 over the square root of 100. And that's going to simplify. What's 10 over the square root of 100 simplify down to?
10. So 1.
So yeah, 10 over 10 would be 1. Okay. How does this standard deviation compare to this one? Which one's bigger? Which distribution should be more spread out? This one or this one? Which one's going to be more spread out? The orange one or the blue one?
Orange.
Yeah, the orange one. This is going to be more concentrated. And in fact, you can see that. And let me just draw it in here. Like that. So the more and more you sample, the tighter this is getting around the true population mean, which is 100. So if you're trying to figure out, like trying to guess, like based on your sample, well, what could the population mean equal? You have a real good chance with a larger sample size of coming close to your population mean. Now, if you're using this distribution, samples of size 10, you can take a look here. There's not as much area underneath this curve. You're not as likely to get close to the true population mean here with the orange curve as you are with the blue curve. So what that's suggesting is that as much as possible, you want to use a larger sample size to try and estimate this population parameter. But that's not the kind of problems we're going to do now. Let's take a look at the ones we're going to focus on. So that's another handout, and I don't think I have that one at home here. They're all at school. So this is a very, very typical example of what we're going to do. And I realize it's not going exactly in chronological order or alphabetical order, but this is the friendly one that I wanted to skip to first. So we'll do example E. Assume that cans of Coke are filled so that the actual amounts have a mean of 12.00 ounces and a standard deviation of 0.011 ounce. So let's stop there and write down some relevant information. X is going to have a normal distribution with a mean of 12 and a standard deviation of 0.11. So in case you're curious what I'm writing, just exactly what I just said. And let's actually maybe draw it as well. While we're here. Oh, that was good. Yeah, don't expect another one quite that good for me here.
That's 17.
Thanks. I don't feel like I want to touch it now. I feel like I should like leave it. All right, so let's draw this line here. This is all for this distribution. It's a normal distribution with a mean of 12 and a standard deviation of 0.11. Like that. What should I label this with right here? What number should I put here for this distribution?
12.
12, exactly. How much of the area is to the right of 12? How much of the area is to the left of 12? Someone else. Someone hasn't had a chance to speak today. How much of the area is to the left of 12? How much of the area is to the right of 12? Nothing? What if there were extra credit to answer? Would you know it then? Still no one?
6 and 6.
Well, the area underneath this curve has to be 1. So you're kind of in the right direction that it does divide it up into 2.
50%.
If the total area underneath this curve is 1, then how much is to the right and how much is to the left?
0.5.
0.5 and 0.5. All right. Just something to keep aware of when you're looking at these things so that if you get an answer that doesn't make sense, that maybe you'll look back at it and figure, oh, I got to subtract from 1 or do something like that. All right, let's go back to our problem. Find the probability that a single can of Coke has at least 12.09 ounces. Now I'm going to change it from what we have here from 12.19 to 12.09. Actually, I should probably change it even to something smaller. How about 12.05? Let's do that. So let's find the probability that X is greater than 12.05. So let me go back here. So part A, find the probability that X is greater than 12.05. Well, it helps to draw these things. So where should I put 12.05 on this number line? To the right of 12 or to the left of 12?
To the right.
To the right.
To the right, so 12.05, good. And so here's my line for 12.05. Which region of this graph am I going to shade, to the right or to the left? Which one corresponds to the area or the probability that X is greater than 12.05? To the right or to the left?
You're right.
To the right. So I want to shade this. This is what I was looking for on one of your problems from the last test, is for you to do this kind of shading. Now to find that area, I'm going to use Google Sheets. But does Google Sheets give me this? Does it give me the area in the right tail?
No, it gives you the left, so you'll have to subtract from 1.
Yeah, well done. It gives you the area in the left tail. So this is what it's going to give me, is this area over here. By the way, based on our discussion earlier, that area in orange, should it be less than 1/2 or greater than 1/2? What do you think?
Less.
I got to vote for less. Does anyone else agree or disagree? All right, so 1-0. The less than 1/2 wins. Good job. Should be less than 1/2 because you're to the right of 12. To the right of 12, you have 0.5 or 50% of the area, and you've got less than that. So it should be less than 0.05. Am I going to use norm distribution or norm inverse to find the area?
Norm inverse.
Do we agree?
You're gonna use norm distribution because you have the value and you're trying to find the area.
Oh.
Yeah. So Skylar's right. You've got the value and you're trying to find the area. So we're going to use norm inverse. So you're assuming norm distribution. Norm distribution of 12.05. And I know that in the problem, this was 12.19, but I don't like the way the numbers work out with that. So I'm changing it. I won't be so capricious on an exam. The mean is 12. The standard deviation is 0.11. What comes next?
True.
True. Nice. Let's do that on Google Sheets.
Did you put 1 minus in the beginning?
You could. I will go back and have to do that. So equals norm distribution of 12.05, comma 12, comma 0.11, comma true. So that gives me 0.6752, 6753 roughly. So, okay. 0.6753, we'll call it. But as I said, before we began this, before we did this calculation, that you expect an answer less than 1/2, and we don't have that. That's because it's giving you the area in the left tail. If you want the area here, I got to do 1 minus 0.6753.
0.3247.
0.3247?
Yep.
Nice. Now you can do that all in one command. You don't have to separate into 2 commands. So what you could do is, you can do a copy. You can do equals 1 minus all of that. Oops, it didn't like that. All right, let me do it this a different way. Equals 1 minus this. There you go. So there's your 0.3247. You could do it all in one command. I'm not sure why it wasn't working there. Equals 1 minus there. Oh, I've got an extra equal sign here. That's why I didn't like it. So if I get rid of that, this command should work. There you go. So either way you want to do it, it's up to you. I don't really have a preference one way or the other. Are we good here with that first part? So this is very typical of these kinds of problems. They give you something that just asks you about a regular normal distribution. You find that probability, all's well and good. Now this is 4 points out of a 10-point problem. Part B is where you earn your money. So let's take a look at part B. And again, I'm going to change the 12.19 to 12.05. So let's go back here. The 36 cans of Coke in data set 26 have a mean weight of 12.05. Find the probability that 36 random cans of Coke have a mean of at least 12.05. And so I'm substituting 12.05 instead of 12.19. But the big thing that's different here is that we're talking about the mean of these things, not the mean of, or not the mean of standard deviation of 1 can. You've got 36 cans. I want to look at what happens to the mean of these cans. What's their average going to look like? What's the distribution of the average? So what changes is I'm no longer working with our parent population. I'm working with a new population. Well, I'm sampling from this for samples of size 36. So X bar sub 36. Well, for samples of this size, it doesn't really matter that I'm sampling from a normal population to begin with. I'm going to get a normal distribution. But what is that normal distribution going to look like? What's the mean of that normal distribution? What's the standard deviation?
12.05.
Appreciate the guess.
For the mean, right?
For the mean comes from the mean of my parent population. So this is my parent population. This is where you're sampling from.
12 and then 0.11.
All right, so it's going to have the same mean, which is going to be 12. All right, so we're good there. So that's the same. And let's just do it this way. Highlight it there and there. Those are the same. The standard deviation is not going to be 0.11. What's the standard deviation going to be?
Is that the sigma divided by the square root of n?
Well done. So here it's going to be the standard deviation divided by the square root of the sample size. So it's going to be 0.11. That's your standard deviation divided by the square root of your sample size, which is 100, or no, which is 36. And that 36 is coming from, well, I'm running out of colors here, right here. So this information is coming from other parts of the problem. Okay. That's going to change this distribution. If I was able to draw this nice and neatly to scale, it would be taller and narrower than what I've got here. So I hate having to do this because this was so beautiful, but I'm going to try and draw another distribution that I can label like this. Well, that one's not too bad. Certainly I've done worse. But this is my new distribution. It has the same mean as before. That mean is 12. And I'm still looking for the area to the right of 12.05. So there's my 12.05. Now it's virtually impossible for me to draw these correctly to scale without, the assistance of this computer. But what I've tried to show is that this is more spread out than this. So if it's more spread out, it's easier to get areas in the right tail than it is down here. So do you think this probability is going to be bigger or smaller than this one up here?
Smaller.
Yeah, it's probably going to be smaller. We're still going to look at it and calculate it the same way. We want to find the area in the right tail, but to do that, we got to find the area in the left tail and then subtract from 1. If you wanted to do it all in one command, are you going to use norm distribution or norm inverse?
Distribution.
Distribution, good, because you got a X value, you want to find an area. So it's going to be 1 minus norm distribution of 12.05, comma 12, comma 0.11 over the square root of 36. And even though that's 6, I'm just going to leave it like this, 0.11 over the square root of 36 just so that you can see where that comes from. And then the last part here is truth. So that's doing it all in one push. Let's see what that gives us. Let's see, all Google Sheets are over here. So I'm going to kind of cheat a little bit. I'm going to copy this. And then for part B here, I'm just going to make one change. Anyone know what that one change has to be?
0.11 divided by 6.
Yeah, 0.11 divided by 6. Well done. So divided by the square root of 36. In case you're curious, you can do square roots this way, SQRT of 36. Or you can just calculate it on your calculator and then type in the number, but it's easiest just to do it this way. So, wow. So I get 0.00319, etc. Are you okay with the calculation of the probabilities? What's that saying about the cans of Coke overall? Let me take a step back and help you put that into perspective. It's saying that while there's a fair chance you can get one can of Coke with a little bit extra, it's very unlikely that that's going to happen with a large number of cans. It's extremely unlikely. You got about a 3 in 1,000 chance of finding even 0.05 of an extra ounce more than what you pay for in your cans of Coke on average. So while it can happen for one easily, it's unlikely to happen for many easily.
I think, oh, never mind.
Got it?
Yeah, I forgot to subtract 1.
Oh, okay. Yeah, because when you first do this, you'll probably get 0.99681 or something like that. So that's the area to the left. And that's why it's really helpful to draw these things. On your last exam, I gave you a lot of these figures already drawn. And it's because I want you to do the shading and I want you to think about, does your answer make sense? Are you getting the right thing? So that's why I put them there, even though I didn't make you use them in all cases. Any other comments on this one before we do another example? All right, let's take a look at, let's see. Let's take a look at example E here. I guess this, oh, I thought I had example E. This one must be mislabeled here. Let me go back. Oh, I guess the previous one I did was example D. So I mislabeled that one. This one is example E. The weights of a certain brand of candies are normally distributed with a mean weight of 0.8586 grams. That's really small. That's really small. Can anyone figure out what candy they must be referring to? What's something with a typically small weight?
Like Skittles.
Skittles is not a bad guess. It's a favorite of your instructors to use in statistical examples, and that'd be M&Ms. But Skittles is a good guess too. So the normally distributed with a weight of 0.8586 grams and a standard deviation of 0.0516 grams. Let's stop and copy that information down right away. All right, so we've got X is distributed normally with a mean of 0.8586 and a standard deviation of 0.0516, and that's in grams. A sample of these candies came from a package containing 464 candies. The package labels stated that the net weight is 396 grams. If one candy is selected at random, find the probability that it weighs more than 0.8534 grams. So, okay. Let's draw some distributions and try and make sense out of all this. So I want the probability that X weighs more than 0.8534. That's the probability we're asked to calculate. And we're going to do that from the distribution that they gave us. So once again, let's draw that distribution. That's this one right here. The middle number gets labeled with my mu. So 0.8586. 0.8586. In relation to 0.8586, where am I going to draw 0.8534? To the left or to the right of that number?
Barely to the left.
Yep, a little bit to the left. 0.8534. So let's draw a little line here. Now, if I'm trying to find the probability that X is greater than that, which way am I going to shade, to the right or to the left?
To the right.
To the right. Perfect. So let's shade to the right. Is that probability going to be more than 1/2 or less than 1/2?
More than.
Should be more than 1/2, because you've got everything to the right of 0.8586, that's half of your area. We have more than that. So you expect something more than 1/2. Am I going to use norm distribution or norm inverse to find this probability?
Distribution.
Distribution. So if I did this, if I did norm distribution of 0.8534 with a mean of 0.8586 and a standard deviation of 0.0516 and true, that's okay. Well, what's it going to give me? Is it going to give me what I want?
Subtract by 1, right?
Yeah, that's going to give me this area here, which is in orange. And instead, I want the area in yellow, so we're going to have to subtract that from 1. So I'll do 1 minus this. I'll kind of color code this. That area in orange is what I get from this command. I'm going to do 1 minus that, I'll get that area. We'll do that all in one step. So let's go back to Google Sheets. So this is example E. So it equals 1 minus norm distribution. By the way, I'm very careful on an exam. I would never give a problem quite like this. Can anyone think of something I might find objectionable about this? Something that you're not liking at this moment?
Swap, you swap the mean and the what they want you to find. They would you exceed.
Did I make a mistake in terms of?
No.
Okay. So 0. It's just all the digits. I hate that. I'm like, okay, I don't want to spend 5 minutes typing these in, and I don't want to see you guys get things wrong because you type in the wrong numbers because they're just so long. So personally, I'd round the numbers a little bit more so you don't have as many digits to work with. All right, so 1 minus norm distribution of of our probability number, 0.8534, the mean, standard deviation, and then true. About 54%. 5401. Now, much like the last problem, the part B is going to say, all right, well, let's now take a sample of these and see what happens.
I have a question.
Yeah, go ahead, please.
So we got, with our calculation, we got 0.5401, but the correct answer on the sheet says 5398. And why is that?
You know,
Because
it's
if we
just
were
such a
doing our
slight
homework,
rounding error that I'm not really worried about it.
all right, I was just thinking, because if we do our homework, it wouldn't be right. So that's why I was like,
I hope that there's a little bit more tolerance for your answers than that. I think I've got like a 3% forgiveness.
all right,
So I hope it's not that critical. When you told me to do that just now, I thought to myself, well, I'm not worried. And that's because I'm thinking about grading your test. But I mean, it's a legitimate concern for the homework.
yeah, because
don't know
usually
why
if you
it's
don't
off in the
get
homework.
it perfect, it's
What's that? You know why? Here's what's happening. The way that they have to do it in the homework, or the way they probably came up with the answers in the homework, is that they're doing it old school. And by that, I mean, what they used to do was they would make you find Z equals X minus X bar over S. So in this case, it'd be 0.8534 minus the mean, 0.8586 divided by the standard deviation. And then that would give you some Z value.
and
I
then
don't
you
know what
find
that would
some
be.
Z.
And then you'd have to look it up in the normal tables to get your value there.
Yeah,
And with all that rounding, you're probably going to get a slightly different area.
yeah, all right. I was just wondering,
So-
because in the homework, it's usually got to be like right on. And I was just wondering.
This should be, in fact, this is more accurate than what you would get if you did it old school. This
All
is
right.
a lot of work. So you guys can feel happy that we're using Google Sheets,
Yeah,
because, I mean, we don't have to do any of this calculation, and people make mistakes on this. And then they get the wrong Z value, and then they look up the wrong Z value, or they make a mistake getting the Z value off the table. And it's just a mess. So I appreciate the question. That should be close enough. I mean, 0.5398 is 3/10,000ths away from the answer that we rounded to. So I'm hoping if it's not, let me know. And I
All
will
right,
look
cool.
into that. All right, so let's finish this one off and then go home, start our break. Says, if 464 candies are randomly selected, find the probability that the mean weight is at least 0.8534. So again, you're changing your problem. Now we're looking at the distribution of the sample mean for samples of size 464. So let me click back to my sheet here. The first thing you got to do is compare this to this and say, all right, well, what's the distribution of this going to look like? Well, for samples that large, one way or another, it's going to be a normal distribution. The sample mean is going to be the same, or the population mean for this is going to be the same as it was for our parent population, 0.8586. But the standard deviation is going to be minuscule. Standard deviation is going to be the old standard deviation, 0.0516 divided by the square root of 464. I don't even think I care what that actual number is. It's going to be really small, because you're going to essentially be dividing this by something close to 22 or 23. And when you divide that by that big of amount, it's going to be really small. The distribution here, if I was able to draw it to scale somewhat correctly, it's going to be really skinny. And the chance of getting something way out here at 0.8534 is going to be pretty small. Not going to be much area to the left of this, although we want the area to the right of this because we're still interested in the probability that X is greater than 0.8586. So we're trying to find this area, which should be more here than it was in our last problem. The command for Google Sheets is still going to be pretty much the same. The only difference is that the standard deviation is now going to be divided by the square root of 360 or 464. It's going to equal 1 minus norm distribution of 0.8534 and then 0.8586 and then 0.0516 divided by the square root of 464, comma, true. The easiest thing to do for yourself here would just be copy this command and change the standard deviation. That's all it really amounts to. So let's do that and we'll call it a day. Let's see, I want to go over to my Google Sheets. So here's my first calculation. I'm just going to copy that over to here. And I'm going to modify it by dividing by the square root of the sample size to get the correct standard deviation. So divided by square root of 464. You need parentheses around either end of that square root. So with that, when I press the enter button, I should get the new correct probability. It's probably a lot higher. If it might even be 1. We'll find out. No, pretty close to 1. 0.9850. Now I will give you a heads up. A lot of problems that you deal with, because they're algorithmically generated, sometimes you'll get probabilities here that are essentially 1. Other times you get essentially 0. That's okay. Those kind of things will happen with your calculations. And if it happens, don't be afraid. All right, just go with it. So in our case, that probability is 0.9850. Comments or thoughts on this last one here?
How do we know that we have to use like square root of 464? Like, what's the keyword?
Great question. The big difference in going from one to the next, let me see if I can't zoom in a little bit for us here. And zoom right here, is that instead of talking about one candy like we did with the first one, so for the first one, we just said, all right, we've got one candy right here. Here we're working with 464 candies and we're talking about their mean weight. So when you start talking about the mean, that's when you're going to use the central limit theorem, that little bit that we talked about at the beginning, where your distribution can be anything. When we start talking about the distribution of the sample mean, it's going to have its own probability distribution. That's this part here. So the first part of these problems is going to say, all right, let's sample from, some distribution. But the second part is going to require you to use the central limit theorem, which is this stuff right here.
Okay.
And your tip off, to be very, very blunt, is it's going to talk about the mean weight or the mean of your random variable. That's the big clue that you're going to be using this part right here. I will tell you that when I grade problems on an exam, the part A here is worth 4 points. The part B is worth 6 or 7, because I want to see that you know how to do this part right here. That's where I'm putting the emphasis, is that you have to understand that when you're talking about a sample of whatever size, Now you've got a new distribution to work with. So, does that help?
Yep.
Great, great. Anything else before we wrap it up? All right, then. Let's put this one to bed.